So, today we will discuss one-dimensional Ising model. So, here we have n spins or electrons or dipoles, okay, in 1D. So, each of them have the spin components plus or minus half, okay, in units of h cross. So, currently what we are looking at is, so there is no external field now that we can do later. So, currently there is no external magnetic field applied to this system. So, only the nearest neighbor interaction. So, each dipole interacts with the nearest one. Okay. So, the question is, we have to calculate the total magnetization, total energy, and the specific heat. So, these are the three quantities we have to calculate for this system. So, this system is in a environment with a temperature T. Okay. So, because it is a nearest neighbor interaction, that means each of them does not interact with the far away dipoles. So, programming is very easy, and basically we have to find out whatever the quantities I told you, that is magnetization, specific heat and average energy under equilibrium. Okay. So, you have to find out those things at a equilibrium condition. So, this is, if you look at, it is basically a quantum mechanical system. So, you can one configuration, okay. So, one configuration of this system can be plus minus etc. Okay, because this plus minus are spin plus half h cross or minus is spin minus half h cross. Okay. Suppose there are n systems, n such dipoles. So, how many such combinations are possible?
N by 2.
2 power n. So, you have 2 power n configurations. Okay. Any question on that? You have a 2 power n configurations. So, so you can write this as configuration S1, general configuration is S1, S2, S3, Sn. So, for example, so this is your alpha I configuration. Okay. So, you are calling this is your alpha I configuration. Suppose the energy for this configuration is EI. Okay. So, energy for this configuration is EI. So, what is the probability to get that, because this is basically a statistical system. Okay. So, you have to now, you can write down the partition function for this. So if Z is the partition function and the system is in an environment with a temperature T, okay, and energy is EI. So what will be the probability for such a configuration? E raised to minus I can call beta is equal to 1 over kT. What is K? Minus beta EI divided by so that is basically the partition. So that is basically what is Z is equal to summation over all EI, right? Okay, then e power minus beta EI. So this is the probability for such a configuration. So what is our job here? What do we want to do? Okay. So our job is for a given temperature, we have to reach the equilibrium condition and then find out the average quantities. Okay. So this is what we want to do. Okay. So for a given configuration, from the so we have to find out for a given temperature what is the equilibrium condition. Okay, and then find out the average quantities. So can you just think about some way to do this? Okay, I just give you 2 minutes. So you tell me how we can do this problem. So question is clear, right? So you have n dipoles interacting each other and they are in an environment with a temperature T. There is a nearest neighbor interaction. So if it is a nearest neighbor interaction, the Hamiltonian for interaction you can write down as H is equal to, because here is only a potential, so what will be the potential, the VI on one particle, one of the dipoles, VI will be equal to minus J SI yeah, SJ should be I plus 1, right? Yeah. Or I minus 1. I minus, so I can take I can take I plus 1 or I minus 1. Okay. So nearest neighbor, because what happens is if I consider the so there are suppose two dipoles. So in that case, if I write down the potential for this one, the first one, you have to just, if I take SI plus 1, the interaction with this is already considered, right? So then there is nothing else to consider for this. So for the second one, because that interaction, because it's only two particle now, so only one potential, right? SI plus 1. Okay. Now if I have 3, so each particle you have to just consider the next one. So next one, if you consider the next one, okay, then we can have the total potential, because that is summation of SI plus 1. Okay. So total potential will be summation of SI plus 1 minus J. So J is basically the exchange energy. Okay. So this interaction is controlled by that J. Okay. So we don't have to worry about the minus 1 if you consider the full potential. So that's what I am saying, SI plus 1. Okay. So that is also given. So now you just tell me, if you just think about it, some of you have already know about this. Okay. So if you already know, don't worry, don't tend to answer. Whoever is first time facing this problem, okay. So I want to calculate the equilibrium condition. Equilibrium condition means equilibrium configuration. I have to reach equilibrium configuration. So I may start with some configuration which is not at all an equilibrium configuration. Okay. Then I have to reach equilibrium configuration. Then thermodynamic equilibrium. Okay. Then find out the averages. So just think about 2 minutes. Do you have any idea regarding this? Yeah?
Do we find the equilibrium by minimizing energy?
Yes. So that is what basically equilibrium means. When you reach equilibrium, the energy, the minimum energy level, right? So we have to minimize the energy. That is what you have to do. Okay. So for that, so what you have to do is, so there is something called a Metropolis algorithm. So what is a Metropolis algorithm? So initial configuration can be anything. Okay. So you take some initial configuration. Then what you do is you flip one of the spin. Okay, there are n spins. Okay, so you flip one of them. Then you so this is S1, S2, S3, Sn. Now the new configuration that you call as alpha trial. Okay, so you are taking that configuration. So you just flip one of them. That flipping can be on anything. That randomly you can choose. Okay. So one of the spin, you actually whatever that some teeth spin. Okay. You flip to minus. So there is a ST. So you flip that one. Then calculate the energy for that. Calculate that energy as E trial. So what will be the probability for that configuration? P of e power minus beta E trial divided by Z. Now calculate the relative probability. That means, suppose, so relative probability of with respect to this one. That means you calculate P of, find out the relative probability P of ETR divided by P of you can instead of E I can write down alpha TR. Okay, energy is ER. Okay, so alpha TR. Alpha I. What will be this equal to? Minus beta E trial minus E I. So this one you call it as delta E. Yeah?
What is this quantity?
Relative probability. See, this one is the first one is the probability to occur the configuration alpha I. Second one is the probability to occur the configuration alpha TR. Okay. So what is the probability to relative probability to occur alpha TR with respect to alpha I? Okay. So if I call this quantity as delta E, so what I am going to get is E minus beta delta E. Suppose your new configuration is having higher energy. Okay. If your new configuration is having higher energy or lower energy, say your new configuration is having a lower energy, what will be delta E? Positive, right, or negative? If your new configuration is having a lower energy correspond with respect to the original configuration, what will be delta E equal to? Negative. If delta E is negative, what will be e power minus beta delta I quantity? It is positive. Okay. So obviously, if the new configuration you are getting is with a lower energy, you have to accept that configuration because you are going to the lower energy configuration. So there is no issue with that. Okay. So if delta is negative, then you accept that the flip. Okay. So that if delta is less than, so let me put the conditions. So if delta is less than 0, you accept that confidence. So alpha trial will be equal to your new configuration. Okay, alpha new configuration alpha new will be equal to alpha trial. Suppose your new configuration energy is higher than the old configuration. What will you do? Obviously, in that case, delta E will be positive. So this will be a number between the relative probability will be a number between 0 and 1. Okay. So that will be between 0 and 1. So the question is, if that is the case, whether I should reject that one or should I put some condition? One possibility is just to simply reject. Okay. But can I do that? What do you think? Should I do that? Is there any problem if I just reject? Because new configuration is going to have a higher energy than the earlier configuration. So I should just reject it. Should I do that? Is there any issue with if I do that?
Flipping another spin might actually reduce.
Yeah?
The further iterations might actually reduce.
No. So see, let us not see. I am not saying that the alpha trial or alpha new you get is the equilibrium. I am not saying that is the equilibrium thing. Equilibrium obviously you have to go for a series of, because equilibrium condition you reach after a lot of iterations. That is true. The only thing is just after one iteration, because you have to think about lot of iteration, right? But before that, one iteration itself, what you should do. One is obviously the new energy configuration is a lower energy, you accept that. Second one is, that is there is no question there. But second option is, if it is a new energy configuration is a lower energy, higher energy, okay, should I reject just like that? Is that physically okay? What do you mean by thermodynamic equilibrium? What do you mean by thermodynamic equilibrium? Can you hear me?
Microstate. Yes, sir.
So when you reach the equilibrium, do you think that there is no change in the dynamics after that?
There is change.
There is a change. There are fluctuations, right? So we can only talk about averages. Okay, you can only talk about thermodynamic equilibrium altogether. Okay, you are reaching a equilibrium temperature. You cannot say that okay, it reached equilibrium energy. You cannot say that so it is reached 2 electron volt. Okay, that energy. So that will stay for 2 electron volt ever after that. It is not true. You can have a fluctuations in the system. So that means in this problem, even after reaching the thermodynamic equilibrium, there is a possibility of flipping of certain spins. Okay, it's a random fluctuation can occur. So even if the new energy level is a negative quantity, new energy is having higher energy than the previous configuration. Now that also you should accept, okay, with some probability. Okay, so how do you decide that probability? That is basically the Metropolis algorithm. This is actually one way of doing this problem. Okay, so it's called the Metropolis algorithm. So in that case, what we do is, so if delta E is negative, delta E is positive, that is basically the new configuration is having a higher energy. Okay, so what you do is because this number you know that in that case between 0 and 1. So you now take consider a random variable between that can give you a uniform distribution between 0 and 1. Okay, then if suppose you make a trial, if that random variable is random number what you are getting in that uniform distribution, okay, you are getting a random number from a uniform distribution between 0 and 1. If that number is less than this number, that is e power minus beta delta E, you accept this configuration. Okay, if that random number is higher than this relative probability, you reject this. Okay, is that clear?
Why do we do that?
That means, see, in the equilibrium condition also there is a possibility of random fluctuations. Okay, right? There is a possibility of random fluctuations. You have to allow that. Even if it reaches equilibrium, obviously there are fluctuations in that. You have to allow that. So even in the new configuration, because even suppose this you already reached the equilibrium, this is already the equilibrium condition. Okay, you already reached. Still there is a chance for something to flip, so that the energy may little bit increase. Okay, there is a chance for that. Yeah.
I understand why we need to accept, but why? What is the logic behind choosing a what is the logic behind this Monte Carlo thing? Why are we choosing a number if it is lesser than you accept?
Obviously, this is a relative probability. Okay, so the probability of obtaining this new this configuration is greater than with respect to some other random process. That's it. Okay.
Why not maybe since I know that once it reaches thermal equilibrium, I know the system, I know that fluctuations will not be major, it will be minor, right? So maybe I put a limit to the probability. I say that the probability of this happening is say 0.99 or something, because the delta E should be like the difference in energy should not be much, right?
Yeah.
Fluctuations can't. So therefore I put a limit to that, and if ETR is within that limit, I accept that configuration.
No, we don't know that limit, no. You don't know it here. You know where is the equilibrium energy. If you know the equilibrium energy, no issue. We are going to find out the equilibrium energy. You are starting this process from the beginning itself. You may be very, very away from the equilibrium. Okay?
Understood.
Okay? So you are supposed to find out that what is that equilibrium energy, average energy. Okay? So this is what you do. Okay? So all of you just take a 2 minutes and understand this Metropolis algorithm. Okay? Then I will explain the next part. Okay, so let me repeat once more. So what you have to do is you take a trial configuration. Initially you take a configuration alpha I, flip one of the spin, you get a trial configuration. Then the energy difference, if it is larger, okay, you go ahead with if energy difference is negative or the new configuration is having a lower energy, you accept that trial configuration. Otherwise, you accept with a probability. Then you keep on doing, so that is the place you are doing initially start in trial, and you keep on doing this. So you can each time, each iteration you can plot the energy. You can see that it may increase, decrease, or you may be started with the very close to the equilibrium condition also. Okay, whatever it is, you see whether it is reaching a equilibrium, and after reaching the equilibrium, you have to do some n prime number of iterations to take averages. So average energy is basically 1 by n prime summation I is equal to 1 to n prime ei. Then magnetization for a given configuration is sum of spins Si, n spins are there. This also you have to average for n prime iterations. The specific heat you can calculate using this formula, U2 minus U square by KT square, where U2 is nothing but 1 over n prime summation I is equal to 1 to n prime Ei square. So this energy square for each iteration. So all these things you calculate after reaching the equilibrium. And yeah, so how you reach the energy. Energy for a given configuration is basically from this formula. Basically, it goes here V, S and S, Si plus 1 are operators. After taking the average using this expectation value, so you get energy for a given configuration is summation I is equal to 1 to n minus 1 Si plus 1 minus j. So this one you have to do for different temperatures, very small temperature up to temperature 5 in units of kT. Okay. Then those details I can give you. One thing you can see that is J is the exchange energy. So J is positive means it is a ferromagnetic material. Okay. If J is negative, it is an antiferromagnetic. So that is known. So you can take J is equal to 1 or minus 1. So you know that at a temperature 0, if J is ferromagnetic, what will happen? All the spin will be So what will be the magnetization at that point? N into 1 by 2. Okay. So this, yeah.
Minus 1 means
Yeah.
you have to change the algorithm. If it is anti-ferromagnetic, you have to change the algorithm, right? Then
No, algorithm is everything is algorithm is same. Okay. Only thing is you have to substitute J is equal to minus 1. Okay. Because what is positive and negative will change now. So this is what you have to do. So before concluding, let me just give you the analytical answers what is available so that you can compare your results.